Hello guys, in this video I'm going to explain the solutions for your assignment 2. Coming to the first question, I have given about skew rays. 1a, explain briefly about skew rays. Coming to skew rays, there are two types of rays in your ray theory. In your optical communication, there are two types of rays. One is meridional ray and the other one is skew ray. Meridional ray is a straight path which will be reflected at the core and cladding interface in this way. Coming to skew rays will travel in helical path. Okay, skew rays will travel in helical path. The major difference between them are explained over here. If you observe this diagram here, you can see that a light ray is being incident into the fiber. Now it has taken one reflection and then one other, and then comes one more and then one more. In this way, your skew ray is going to be traveling. These rays are your skew rays. The graphical representation of skew rays in optical fiber is as follows. Skew rays are not confined to a single plane. That is, they are not confined to a single plane. That you can't represent skew rays in single dimension. Coming to meridional ray, you can represent them in a single dimension. That means if you are seeing this ray in a single dimension, you will observe this as a straight line. If you are seeing this in a two-dimensional path, you will be observing this traveling in this dimension and in this dimension. That means this direction and this direction. If you want to observe this in a single direction, you will be seeing it like a straight line. But coming to skew rays, you can't see them in single dimension. Okay. Skew rays are not confined to a single plane. Skew rays will not touch the fiber axis. Instead, they move around the axis with each reflection. Here you can observe that with each reflection, they are traveling around the fiber axis, but not at the fiber axis. This has been illustrated in this figure. Here you can observe that at the point of core and cladding interface, if there is an interaction of skew rays, light ray with this core and cladding interface, it has taken a reflection. Again, there is one more reflection, another reflection. So in this way, it is going to travel around the point of interaction between core and cladding, but it is not going to travel through the axis. Oh, these rays follow a helical path. If you can observe this path, it is helical in shape. Okay, like we have drawn it previously, it is going to travel around the axis and then it is going to move forward. Again, it is going to travel around the axis and move forward. Okay, it is going to move forward by traveling around the axis. The helical path traced through the fiber gives a change of 2 gamma. This is 2 gamma. As the wave is traveling around the path, it is going to have a change of 2 gamma. This is gamma with respect to a perpendicular, and there is one more. When it has interacted over here, it is going to undergo change of gamma. So both combined, we are going to have 2 gamma in the direction of propagation at each reflection. Gamma is angle between projection ray in 2D and radius of the fiber core at the point reflection. Here you can see it is the angle between radius of the fiber core and the projection. Okay. The point of emergence of skew rays from the fiber in air will depend on number of reflections they undergo rather than input conditions of the fiber. Here, what do we mean by point of emergency is the point where the light ray is coming out of the fiber. If you have taken this, if the fiber is ending over here, then this is the point where it is coming out and it is known as your point of emergence. Okay, this emergence depends on the number of reflections it has undergone. Let me say if the fiber ends over here, instead of this reflection, it has ended over here, then your light ray will be traveling in this direction. If it has ended over here, your light ray will be traveling in this direction. It will travel in this direction. If it has ended over somewhere over here, it will be traveling in this direction. Okay, so depending upon the point of emergence, light rays will come out of the location. That means the number of, if it has undergone one more reflection, its direction is going to change. But it is not going to depend on the input conditions. If light input to the fiber is non-uniform, skew rays will tend to have smoothing effect on the distribution of light as it is transmitted, giving more uniform output. For example, if light input is non-uniform, that means it is traveling in different directions. Okay, it is traveling in different directions, then it will all undergo some reflections, and you're going to have, every light is going to have undergone some reflections, and it is going to form a uniformity of shape inside the fiber. Okay. The following figure is used to calculate the acceptance angle of the skew rays. Like we have seen in meridional rays, if a light ray is traveling in this way, if a light ray is being incident and then it is traveling in this way, then we have called it as meridional ray, and for this we have calculated numerical aperture and acceptance angle. But for skew rays, we haven't calculated any acceptance angle. Here we will be observing the acceptance angle for skew rays. As the incident and reflected rays at the point B are in same plane, it is considered as cos phi. Here you can observe, this is the incident ray and the reflected ray. They both are in same plane. If you can observe here, there are different planes. This is one plane over here. You can observe, this is A, T, B, and this location. This is one plane over here, and there is one more plane over here. Okay, there is one more plane over here. So you have two planes over here. In this, you can observe that the incident ray and the reflected ray, these two are in the upper plane. There are two planes. Let us represent this as upper plane and this one is lower plane. The incident ray and the reflected ray, these two are represented in upper plane. Okay, so they are present in single plane. Hence it is represented as cos phi. If the two perpendicular planes through which the ray path AB traverse are considered, then angle gamma is the angle between core radius and projection of the ray onto the plane BRS normal to the core axis. Here you can observe, here is your B, here is your R, and then comes your S. Okay, now what we are saying is, after incident, if it has traversed a path which is perpendicular to the plane, this one is your plane, normal plane. If this is your plane on which you have your light ray, on which it has inserted, and now it has going into another plane, and this plane is present in this dimension. If there is a plane in this dimension, this plane and this plane are perpendicular to each other. Hence, we are telling that there is an angle gamma which is being subtended over here. And theta is the angle between the ray and a line AT drawn parallel to the core axis. Here you can observe theta is the line drawn between the plane and the core axis. Okay. Thus, to resolve the ray path AB relative to the radius PR in these two perpendicular planes requires multiplication by cos gamma and sin theta. Here, in order to solve this, as we have said, in the same plane we are using cos angle, and if there is a perpendicular, then we are using sin angle. So theta is associated with sin and gamma is associated with cos. Okay. Now the reflection at point B at an angle phi may be considered as the reflection at point B at an angle phi is considered as the product of cos gamma and sin theta. As we know that according to this identity, sin squared phi plus cos square phi is equal to 1, we are using this identity and converting this cos phi into 1 minus sin square phi and root. Okay. If the limited case, if the limiting case of the total internal reflection now considered, then phi becomes equal to critical angle phi c. We know that critical angle is the angle above which it is going to, the ray will be shifted from one plane to another plane. So we are considering critical angle as your limiting angle. It is considered as cos phi. So cos phi is your critical angle. If the two perpendicular planes through which ray AB path traverses, okay, this is previous one, here you go. then phi becomes equal to critical angle phi c for the core cladding interface. According to Snell's law, sin phi c can be written as ratio of reflective index of core by ratio of refractive index of cladding. Sorry. Critical angle formula has been written as ratio of refractive index of your cladding to ratio of refractive index of your core. Here, generally, your Snell's law is identified as a product of refractive index with sine angle of incidence is equal to refractive index product with sine angle of reflection. Here, what we have considered is at critical angle, what we are expecting is if a light ray is being passed from this, and this is your angle of incidence, theta I, and you have a light ray over here, and you have a light ray over here. Now what you are doing is you are changing this angle such that this light ray is going to be traveling in this direction and finally in this direction, and finally it will align with the axis. Or you can observe that if you are incident over here, you will be having a light ray over here. Now what you are doing is you are changing this angle so that it will be closing in this direction. Here it will be closing in this direction so that it will be coming back to the same plane as that of incidence. Okay. Now at the point where this light ray meets the perpendicular axis is known as your critical angle. At this point, if you can observe this angle, it becomes 90 degrees. Okay. So sine angle of 90 degrees becomes 0. So in general, this is the formula for your sine theta c critical angle into n1 is equal to, according to Snell's law, you can write this as sine theta r reflected into n2. Now your theta r has become 90 degrees, so you will be removing this theta r. Hence you have only n2, and this n1 has been sent here. Hence you are going to have sine theta c is equal to n2 by n1. Now coming to the previous formula, using the previous formula, you can write this as a cos phi c. Okay, this became cos phi c. Instead of sin phi c, you are writing n2 by n1, replacing these values in your previous value. Here, instead of sin phi, you are writing n2 by n1. Okay, by applying Snell's law at point A, we have n0 sin theta is equal to n1 sin theta 1. Here you can observe, here is your point A, here you have theta and theta phi. Okay, so here you will be applying this. So here this AS is the acceptance angle of your skew rays, where theta A, but generally if you are talking about meridional rays, theta A is represented as the maximum input angle for meridional rays. Theta is the internal axial angle. Hence, substituting sin theta from equation 3, using sin theta from this into equation 4, substituting over here, we have sin theta AS is equal to n1 by n0 cos phi by cos gamma. Okay. So what happened is here we have sent this cos gamma this side, you will be left out with sin theta. Using this formula, instead of sin theta, if you consider this as sin theta A, okay, so you becomes this sin theta has been represented as n0 by n1 sin theta A. So now what happens to this formula is, here you can observe this formula. This is written as sin theta is equal to or less than or equal to cos phi c. Okay, cos phi c. This becomes less than equal to cos phi c by cos gamma. Using this, sin theta is replaced with n0 by n1. Okay, you have removed this. So sin theta is replaced with this formula that becomes A, and this n1 goes to top over here n1, and this n0 comes to the denominator over here n0. Okay, this is what you have observed over here. Instead of A, we are writing AS because we are using theta A for meridional representation and theta AS for skew ray representation. Okay, now it has become in this way. We know that cos phi c is equal to 1 minus n2 square by n1 square. So we are replacing cos phi c with 1 minus n2 square by n1 square power root, and then comes the other formula. Okay, this has been replaced with this one. Hence we have obtained this equation. Okay, where theta AS now represents the maximum input angle or acceptance angle for the skew rays. Now coming to the second question in first one, 1B, explain about numerical equilibrium numerical aperture. Generally we learned what is numerical aperture. In this we will be learning about equilibrium numerical aperture. This refers to numerical aperture with respect to extreme exit angle of a ray emerging from a fiber in which equilibrium mode distribution has been established. Okay. What do you mean by equilibrium mode here? What we are talking is extreme exit angle of a ray. If you have considered a fiber over here, if you have taken this to be a fiber, in this, the angle with which the light ray has been exiting. Let me say, if this is the light beam that is coming out, this is the light beam that is coming out. This is the extreme angle towards this side direction, and this is the extreme angle towards this direction. So you here, this numerical aperture is dealing with the extreme angles, exit angles. Now, if the input mode, the mode of the input signal is equilibrium mode. What is equilibrium mode? We have given over here. The equilibrium mode distribution of a light traveling in an optical waveguide or a fiber is the distribution of light that is no longer changing with the fiber length or with the input modal excitation. So let me say, if a light ray is being traveled, its properties are changing due to microbending, macrobending, scattering, and many other attenuation parameters. Its mode is being changed. Let me say, initially it has started as a 0 mode. Later it has converted into single mode, 2 modes, 3 modes. So the number of modes are being changed because of the internal attenuation parameters. Now what we are saying is a mode is said to be equilibrium, or a wave mode is said to be equilibrium in nature if it has not gone any change as it traveling along the fiber or with input modal excitation. Even though you have changed your excitations, keeping your mode constant, that means if you are varying your intensity, even though you are varying your intensity, its mode should not change. As it is traveling along the length of the fiber, even though there are any repercussions inside, it should not change. These kind of light modes are known as equilibrium modes. That means what we are assuming is, in order to calculate equilibrium numerical aperture, we are assuming that there is no change in the mode of the light. That means we are assuming that the signal which we have sent into the fiber is coming out of the fiber exactly. Okay. The light source has a short fiber fly lead attached to it in order to facilitate the coupling of the source to a system fiber. For example, you have a fiber over here, you will be having a connector over here. After the connector, you will be having small portion of the fiber. In order to use this to connect this to the transmitter or receiver which is present over here. This will be inserted into this transmitter or receiver. Okay. And the small portion which is present beyond the connector of the fiber is known as fly lead. Okay. Small portion of the fiber which is left outside the connector in order to make the or facilitate the coupling of the source to a system. System is transmitter or receiver. Okay. In order to have a low coupling loss, this fly lead should be connected to a system fiber with identical numerical aperture. Okay. Here you are considering a new fiber to join with the previous fiber. In order to have the low coupling loss, what should we do is, this is the system fiber at the transmitter side. This is a system fiber which is coming out of the system, and you are connecting a new fiber to this. What is the parameter required is identical numerical aperture and core diameter should be present between these two fibers. At this junction, certain amount of optical power, approximately 0.1 to 1 dB is lost. At this point, due to connection loss or splicing loss, you will be losing 0.1 to 1 dB. The exact loss depends on method of connecting. What is the method of connecting? Whether you are using a splicing technique or connector. Also, excess power loss occurs due to non-propagating mode scattering out of the fiber. And there are other losses which are due to scattering of light out of the fiber. The excess power loss is to be analyzed carefully in designing an optical fiber system. This excess loss is shown in terms of fiber numerical aperture. So if there is the excess loss, instead of these losses, if there is excess loss, that is light which is being lost in this, should also be analyzed. Numerical aperture at input light acceptance side is denoted by NA input. So at the input side or at the input fiber, it is denoted, numerical aperture is denoted as NA. Here it is NA in. Okay. When light emitting area LED is less than fiber core cross section area, then power coupled to the fiber is NA is equal to NA in. Okay. What do I mean is, if an LED is emitting light, this is, let me assume that this is the LED output and the LED is emitting light in this way. Your LED is emitting light in this way. If you have a fiber of this radius, your complete light will be occupied into the fiber. So if this is the numerical aperture NA in of the fiber, then numerical aperture of the LED will be equal to this because complete light has been occupied. If the optical fibers are measured in long fiber lengths under equilibrium modes, the effect of equilibrium numerical aperture is significant. That means after a long distance, you are considering equilibrium modes. The effect of equilibrium numerical aperture is significant. Hence, we are writing a formula. Optical power at this point is given by optical power at a point of 50 meter length. Okay, P50 is 50 meter length, is given as input numerical aperture and numerical apertures ratio, equivalent numerical apertures ratio. What is equivalent numerical aperture? It is the numerical aperture measured when an equilibrium mode waveform is being traveled. For a long distance, it is taken out as a ratio of your input numerical aperture because it is not an ideal case. So in practical case, there will be a loss. Hence, we are considering the ratio between ideal equilibrium numerical aperture and the input numerical aperture. And we are multiplying this with a power which is present at a length of 50 meters. Okay. In order to calculate power which is present at the equilibrium mode at the output, where P50 is the power in the fiber at a 50 meter distance from the numerical aperture at the launch. This is the launch. At the 50 meters, you are calculating the power and you are multiplying this with any distance. The degree of a mode coupling is mainly decided by core cladding index difference. Most of the optical fibers attain 80 to 90% of their equilibrium numerical aperture after 50 meters. Hence, numerical aperture, equilibrium numerical aperture is important while calculating launched optical power in telecommunication systems. So equilibrium numerical aperture should be calculated in order to know the overall equilibrium numerical aperture of your fiber or overall numerical aperture of the fiber. This is estimated with the help of a fixed power value that we have taken at a distance of 50 meters after launching. And then we will be using this to calculate the power present at any given point using that particular numerical aperture.